So the things that you guys are pointing out are the things that I'm wanting you to recognize for these different characteristics of these waves. So what y'all are pointing out actually has a name, and it is called wavelength. So these all have a different wavelength. So I want you to write down the definition of what a wavelength is underneath your number 1. And I do want you to write the whole thing, that distance from any point on a wave to an identical point on the next wave is what wavelength is. And do go ahead and add in that the shorter wavelength has more energy. The shorter wavelength has more energy. And I'm going to let you write for a second, and then I'm going to talk, because I know sometimes it's hard to write and listen at the same time, and I want to make sure you get it all. Once you guys get that, we are going to actually draw these together. Draw or sketch? Sketch.
Are those your science glasses?
These are my computer glasses.
Those are your glasses.
She has like these big old science glasses, these reading glasses, computer glasses, sunglasses.
Everyone good on this definition?
It's Iron Man glasses.
So the first thing you're going to draw is a transverse wave. So if you want to go ahead and do that, I'm going to make about 3 humps in it, as Gannon calls them. They're actually called crests, and I'm going to teach you that right now.
Called Patrick's.
I'll go back to this.
Can I draw like this face?
Okay, so what I want you to do is draw a transverse wave that looks like mine, or has about 3 humps in it. 1, 2, 3.
You got 3 cracks.
This is a transverse wave. Now, transverse waves have certain characteristics about them to help us identify them. So one of those things are called crests. So anytime that you're looking at the top of a transverse wave, it is something called a crest. So I want you to label the crest.
Patrick.
And I remember crests sometimes because it reminds me of like a crescent moon, and a moon's in the sky, so it's up high. So anytime you're looking at the top of a transverse wave, it is a crest. Yes, Gannon?
It reminds me of the crust on a pie.
Okay, crest on the pie is on the outside, on the top.
Can they be different sizes?
Yes.
Higher,
Yes. We're going to talk about that actually in just a minute. Anytime that I'm looking at the bottom of a wave, of a transverse wave, it is a trough. So these bottom pieces here are troughs. T-R-O-U-G-H. T-R-O-U-G-H. Trough. Make sure you're labeling yours as well.
Isn't that like a candy or chocolate or something?
Trough? I don't know. Now, remember we're talking about wavelength, because that's what you just wrote the definition down for. And what you wrote was the distance from any point on a wave to an identical point on the next wave. So, if I'm talking about a transverse wave, and you might even want to make a note that this is only for transverse, but you just drew the transverse wave, so you could always just look at it. Transverse. When I'm looking for a wavelength of a transverse wave, it is always a crest to a crest or a trough to a trough. What were you going to ask, Sam?
So is the wavelength only for transverse waves?
It's for both, but to find wavelength for both waves is different. So I'm showing you transverse right now. I'm going to show you longitude next. Okay, and did you write this down?
I gotta glue the front of my mask because the fuzz is all getting in my nose.
So go ahead and write down from the crest to the crest or the trough to the trough is a wavelength because it says from any point on a wave to an identical point. So trough to trough would be two identical points on this wave. There's also something else in a transverse wave. And sometimes it's a straight line all the way across, and sometimes it's dotted. I always do a dotted line, so you can do dotted or you can do straight. But it's right here along the center. And it's always the middle, but of course I'm not measuring it out to find the exact middle. But this is called the rest position. And I remember rest position because I'm like, well, if I turned this wave off, like if there's a way for me to just like turn it off, I feel like it would just like shut in the middle. So it's that meeting spot in the middle, so very center of the wave. So as of right now, you should have labeled your crest, you should have labeled your trough, you should label those two wavelengths that we see, and then this could even be a wavelength too. And then label your rest position.
What does the wavelength have even? Is it important?
It is important because what did I say about a shorter wavelength? You guys wrote it down a second ago.
Energy.
Shorter wavelength has more energy.
How do you know? Are we gonna like measure and be like, this is
Well-
2.5?
Well, guess what? Here's one wavelength here. Let me give you an example. Shorter wavelength has more energy. I'll draw another wave.
That has more energy than that.
Gannon, are these two wavelengths the same?
Do we draw that?
No, you don't have to draw this.
No, that one has more energy. But like, how are you supposed to know? Like, what if it's cutting it close? You're gonna get it out of the room.
Sometimes there'll be numbers on it. Like it'll say like this one's 3 and this one's 2. If it's ever that close.
It's like the reason
Does the height?
Hold on, Gannon. What?
is the reason why it has more energy because they're like more pressed and more troughs.
Yes,
Does
because that makes more wavelengths. But to me, when I look at this, so if I had like my rest position here, I'd be like, this one just looks like there's more going on to me. Because like there's more crests and more troughs. Those wavelengths are closer together. This one kind of looks like it's like da 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 da. This one's like woo, like all over the place. So more energy is in this wave because it's occurring more often. And
Does it matter how tall it is compared to others?
it does matter how tall it is, and we're going to talk about that in just a second. It does. Right now it does not, but in a few minutes it does. Any other questions about wavelength for a transverse wave? This is how I find wavelength for a transverse wave.
How do we find the wavelength for like if it's like higher or lower?
That's a different scenario that we're not going to have to do. So you're not going to have to find the wavelength of those.
I wanna know.
You would find an equal one to an identical point. So if it was like all crazy, blah, 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 you would try to find the ones that are identical.
Is there any,
That don't look identical.
If there's not any, then
Wait,
there's not a set wavelength.
is there any way that they could be like really small and skinny and then like get really long?
But we're not going to deal with those in class. So, yes, but
We're thinking
not
two science.
now. Yeah, y'all are taking it really deep, which I like, but we don't have to actually do that right now. So, we're going to learn the basics first, and then we'll get to the more difficult stuff. Good on this one. Can I erase this one?
Yes.
Okay. Let's do a longitudinal now. Longitudinal. So we're going to draw a longitudinal wave.
I understand.
You're probably going to want your wave to look kind of like mine so that your descriptions look the same. So my drawings now, I'm going to do some that are close together. Because remember, you send that big burst of energy. And then I'm going to start spreading them out. I'm going to do one more close together. And remember, my drawings are not the best. Okay. Similar to that. So you know how the transverse waves, they have a crest and a trough and a rest position. Those are specific to just transverse waves. Now here's some things that are specific to just longitudinal waves. So this one's longitudinal. And a longitudinal wave has something called a compression. Where do you guys think that is? Remember from yesterday when we kind of talked about it a little bit? The squishy parts, the compressed parts. So this right here, I'm actually going to make this like parentheses, is called a compression. The compression of a longitudinal wave is the part that is compressed. It's the part that's squished together. So a way for you to remember that, compression, compressed. So go ahead and label the parts that you drew that are squished together, that are compressed together. There's another part of the wave called a rarefaction. A rarefaction. A rarefaction is the part that's spread out between. So this is a R-A-R-E-F-A-C-T-I-O-N, a rarefaction. So similar to how the transverse wave has a crest and a trough, a longitudinal wave has a compression and a rarefaction. Okay. Do you need to get one from the library?
Trying to figure something.
Do you want to go down there and get one from them?
Is it not dressed in?
Oh, I don't know. Actually. Maybe if you tell them like what's going on.
Yeah, I ain't going on there. Let's shove a piece of paper.
Now, wavelength. Remember, that's what we're looking at. How do you find a wavelength for a longitudinal wave? Well, let's go back to our definition of what a wavelength is. A distance from any point on a wave to an identical point on the next wave. What would you guess that maybe a wavelength would be? What would a wavelength maybe be for a longitudinal? Any point to an identical point. All of what? Okay. So any beginning of a compression to the next beginning of a compression. Or any rarefaction, and I'll draw it
What do they call it?
to the next rarefaction.
You hear me?
Or if I start at the end of the compression, it'll be the end of the next compression. Any identical point. So it's a whole rarefaction and a whole compression. So this is your wavelength here. So now you've learned wavelength and what it is. And we know that a shorter wavelength has more energy, but wavelength for longitudinal and wavelength for transverse look a little different. So you got to keep that in mind. I'm going to give you some cheat codes here. Gannon, you want some cheat codes?
I'm trying to figure this thing out. I'm done.
Write this underneath all of this information. Gannon, right, stop talking, please. Take it out. For a transverse wave, here's a little cheat code for you. A wavelength is a crest to crest or trough to trough. You might want to write that down. Crest to crest or trough to trough.
I'm confused about what is the wavelength in there?
So a full compression and a full rarefaction. The beginning of a compression to the next beginning of a compression. Or the beginning of a rarefaction to the next beginning of the rarefaction. Whole compression, whole rarefaction. That's your cheat code for a longitudinal. A longitudinal is a full compression and rarefaction. So you might want to add that into your notes so you have it like to look back to just real quick if you ever need to. So now that you know this terminology about these, we can actually start talking about them. Because I can be like, well, look at the crests of these transverse waves, or look at the troughs, or I can say, look at the wavelength of this longitudinal wave. This is going to help us communicate about these waves. Once you guys get all that, I'm going to put the screen back down.
Wait, can you hold up?
I can. Just me writing. I'm not the English teacher, I'm the science teacher.
Every time I try to breathe it,
Everyone good?
paper sticks to my
Shannon, are you good on this?
not good for my
Is there any questions about it? Not understanding a part? You're good? Okay. Sam, you ready?
Yeah.
Alright, so here's those pictures that we were just looking at. Makes a lot more sense now that I explained it, right? Than just looking at some random picture that has a bunch of words on it. So we're going to write number 2 now. So this is going to be number 2. Oh, sorry, there's a question here. Which one has a greater wavelength? Greater wavelength. What is a wavelength of a transverse wave?
trough to trough or crest to crest.
From trough to trough or crest to crest. Which one has the longest? Z. Which one has the most energy?
Wow.
Y. Good.
Because it's so rapid.
Number 2. Wow. Love this thing.
No, you don't.
Oh my goodness.
Whoa, whoa,
Stop
whoa.
hacking. Where are you going?
Number 2, what's different about these waves? Talk to a neighbor if you want to. Talk to somebody. You're going to have 1 minute. Write something down. So you should skip a line probably and put number 2. Sam, did you have a question?
No.
Oh, you're going to answer.
I have a question.
Yes, Cannon.
I've never seen it before where like it goes from the side and it don't show the end.
Yeah, don't worry about that. Just focus on this part. What's different about these 2 waves?
They be like
Don't tell me about just one wave. I want to know what's different about the 2. Make sure you're paying attention to the question. Write down for number 2 on your paper.
what's the same about them.
What's different? What's different?
Do we do it on properties?
Yep, under number 2. Because remember, we learned about wavelengths for number 1. Karen, why don't you go to the library and ask them?
I don't even think my parents would care if I slept through this.
I mean, just go ask them and say, I'm having a hard time. You have a mask. You just need a replacement.
Take out the paper, though.
No, take the paper. Just do what you gotta do.
They're gonna be like, "What you looking like?"
Put the paper back in there if it helps you breathe.
It doesn't help breathe. It helps not flood.
Okay, share me some things. Share with me some things. Yes. S has higher crest. There are different heights on number 2. When you say heights, are you talking about the crest? There's different crest heights. Delanna, did you have something different? Same thing. Anyone put something different than that? The spacing between the 2 are different? Okay, that's true. Anything else? Okay, what you guys are saying is correct. So, there are different heights here, yes? Yeah. You see all those different heights? Yes, I'm
So do I just go to the library?
Yeah, just go to the library and you'll walk in and you'll go find a librarian and say, hello, I need help.
You have to walk the 7th grade.
Only 4 minutes.
Oh, wait, do you?
Yeah.
Oh, it's fine, just go.
Leave.
He's in my mom room. So what this is called amplitude. This is called amplitude. So you're going to write a definition for it just like you did for wavelength. The amplitude is the maximum distance that the particles of a wave's medium vibrate from their rest position. Who knows exactly what that means right now? Probably not.
Me.
You do not have to know what that means at this moment. When I explain it to you, it's going to help. Yeah, if you run out of room, just turn the page. I wouldn't page number because I'm going to keep going through as the pages are going. So if you just want to say this is still 13, even though you wrote on multiple pages, it's fine. And go ahead and add that a larger amplitude has more energy. A larger amplitude has more energy. And we're going to talk about this one, and then I don't think we're going to get to the next one in class today, so we'll have to finish it tomorrow before we do our little lab rotations that we're going to do. But once you get done writing this definition, we are going to draw another transverse wave. And you might want to make a note that amplitude is only for transverse waves. Amplitude is only for transverse waves. I'm going to pull this up a little bit so we can start writing mine. Amplitude is only for transverse waves. And if you're already done writing the definition, go ahead and draw a transverse wave. And I'm going to put about 3 crests in mine, so you might want to do the same. Everybody good on this one? Ready, good? You good to go? Okay, transverse wave. And I'm going to go ahead and add in my rest position real quick. Guys, remember that's there. Sometimes it's a dotted line, sometimes it's a straight line. And I'll label it even rest. I'm just going to put rest this time. So let's go back and look at that definition really quick. It says the maximum distance. Maximum means the biggest distance that the particles of a wave's medium vibrate from their rest position. Okay, let me take out the parts I know. Maximum, the biggest distance from the rest position. So what amplitude is, and remember it's only for a transverse wave, is from the rest to the crest. That's a cheat code for you. You might want to write rest to the crest is what amplitude is. But it does say that it's from any distance from their rest position. So it's also the rest position to the trough. It just doesn't rhyme as good. So rest to trough as well. So go ahead and label those two, and we'll have to get back to them tomorrow whenever we start class. And someone will have to remind me that this is where we stopped yesterday.
Open the.
And you may pack all your things up, and you may leave once you are done because
I got one.
Good. So for amplitude, you have from the resting position up to the crest, or you have from the resting position down to the trough. And these are only for transverse waves. There's not an amplitude for longitudinal waves. So just the transverse wave that looks like this. The next slide that you guys have asks you to say which one has larger amplitude, wave S or wave T. Wave S would have a larger amplitude in that question. The next slide shows you a red line moving and a blue line moving. So if you're looking at that slide, you can see the red line moving and the blue line moving. I want you to take a second and I want you to look and think what's different about those two waves. So look at the differences between the two, and what do you think is different about the two? Okay, so you should have noticed something along the lines of The red one was kind of like, they were moving at the same speed, but the red one had less tops and bottoms and crests and troughs. But the blue one had a lot, and it was going along the bottom, so it might have even made it look like it was moving faster. This is called frequency. So how frequent the wave is occurring. And the definition of frequency is number of waves passing through a point at a certain time. And this is also just for transverse waves. So you might want to make a note of some kind that frequency is for a transverse wave. So the higher the frequency, the shorter the wavelength. The higher the frequency, the shorter the wavelength. And I will draw an example of that. The higher the frequency, the shorter the wavelength. So, frequency we just said is the number of waves passing through at a certain time. So if I have these waves here, and then I have these waves, which set of waves has a higher frequency? These waves. Because there are more of them passing through at a certain time. And I'm going to go ahead and put dots up here to resemble my crest. That way I know like how many crests I'm looking at here. Higher frequency, shorter wavelength. Well, if I'm looking here, my wavelength of this wave is this long, and my wavelength of this wave is this long. And we just said this one has a higher frequency. And it's occurring more to me. It's more frequent. So it does have a shorter wavelength. And that's just something that you can look at it and see. And if you're ever needing to kind of have a visual of those, just go ahead and point out your crest or your troughs and just draw those lines and make those